Thank you, everybody, for your patience and for coming to the first of many events this week. As you know, we're here at the Fund Conference. It's been around for 20 years now, and if everybody gets a chance, take a look at the poster that's outside and come to every single other event that will have fewer technical complications. We have here today Jan Krymsky of Canada Design. Jan's the senior designer at Krymsky Studio, and he heads up the responsive skins research. Graduating from USC, Jan's professional career is focused on the advancement of architectural design by intersecting conceptual ideas with computational technologies. And he's been recognized by the AIALA, the Chicago Athenaeum, and has appeared in publications that emphasize facade innovation and emerging visual practitioners. Currently, his work focuses on building data-driven architectural systems which hybridize mass production and customization as innovative design solutions to present realities of architecture and construction.
You didn't write that.
Thanks.
Thank you. So thanks for having me tonight. It's a real pleasure to be able to get out of the office and talk to some people. I'm not the guy that's the polished presentation guy. I'm the guy that's usually in the desk doing the work. So it's bad news and good news for you guys. A, I'm not a good presenter, but B, I know all the answers to most of what I'm showing you. So if there's anything that you want to get into the details on, feel free to ask. I would prefer if this was a kind of interactive, more of an informal session where we can have a conversation, if that's possible. So what these guys asked me to do is to give you guys about a 1-hour presentation and then kind of a demonstration. And if any of you want to follow along with that, that's cool too. The demonstration part, I don't know about that. That's going to be a little tricky because Grasshopper on a little laptop monitor without, I'm used to kind of a much bigger setup. But we'll see how it goes. So I wanted to talk to you guys about basically my experience over the past 15 years, how I've seen the profession change since I've graduated. I don't plan on making any kind of grandiose statements or anything like that. It's really just my experience, what I see happening, and how that's affected our practice. So I think the most significant thing that's changed since I've started is a kind of an attitude about mass production. When I started practicing, everything that was something that we tried to do in terms of design came back to the idea of repetition. Because repetition meant it could be developed and it could be built cost effectively. And it's really this outgrowth of the Industrial Revolution and the concept of modernism. And that idea has started to change a little bit. The idea that you can have lots of little components, and all those components can be incredibly intricate, but it's the same piece over and over and over again. That no longer really holds true because digital fabrication is allowing us to make independent individual parts, each one slightly different than the next. And then really the thing that this has changed is the fact that complexity doesn't necessarily equal cost. It used to be that if you were doing something that had lots of one-off parts, little individual things, that was going to be expensive. That's no longer the case. If you have the know-how, then complexity doesn't necessarily equal cost. It really just means that there's human intelligence behind it and a kind of understanding of how digital fabrication can be used to develop very, very complex things. So the word complex isn't really a bad word anymore. It used to be like complex is kind of terrible. It's going to be expensive, it's wasteful. Complexity is no longer, at least in my mind, complexity is not a bad word anymore. So now that we have complexity, how do you manage complexity? It's not that data is hard to come by. Data is everywhere. We have software that's giving us data, we have demographics data, we have the internet. Information is all over the place. But what do you do with that information? How do you parse it? How do you organize it? How do you make it useful? And that's kind of where I want to focus the talk, is since we've started to delve into this kind of research on facades and looking at complexity, what we've discovered is to be successful, you have to know how to deal with tons and tons of data, how to organize it, how to visualize it, how to manage it, how to rationalize it, all of the above. So, wow, I barely see the stuff on the right, but whatever, it's cool. These are 2 old competitions that we did, and I put them up there. They're actually from that one's for 2001, before there was even V-Ray, and that one is 2004-ish. The reason I put these up here is because they kind of show you the kind of designs that we've been trying to achieve. And you can see the attitude is all about repetition. There is a hidden formula in both of these skins where there's a pattern that's repeating over and over and over again. We're trying to make it look like there is no pattern. We're trying to get away from that kind of Miesian, repetitive office building look. But at the same time, we're trying to do that in the context of a manufacturing process that's based on a part that gets repeated over and over and over again. This is a lab project that I worked on in Boston, in Buffalo, sorry. And it's also one of those buildings where you can see that we've sort of cleverly tried to mask the fact that it's really a pretty basic system. It's repeating over and over and over again. It's a Century metal panel on the exterior, insulated metal panel, and it has actually the glass, the windows that are inset into the curved facade there are flat. So they're not curving with the building. So we've sort of cleverly tried to create something that looks non-repetitive and unique, but we've done that in a way that suits a manufacturing process that we thought existed. And I think at the time it did. It was a true piece. It was a reality. And that's views from the inside. I put this image up because we always have this problem when we do this kind of variegated facades. Where we have a pattern on the exterior, we really want it to be repetitious, and we want to create that texture. But then there's always a compromise. There's always a place where you want to have a big window on the inside and a small window on the outside. And how do you resolve that? With a system that's based on repetition, it's less flexible. But if you've got a system that has a lot of components, a lot of variation that's possible, then you can deal with situations like this. So another project, it's an example of kind of same facade system, same approach. This is on the Dominguez Hills campus in California. Oh, and then something where we start to move into this place that I'm talking about, into the world of digital fabrication. We didn't know we were going there, but it started to become a reality. This is a hospital and lab. It's a hybrid building in Buffalo. It was just completed last year, the construction was. What we realized was that the manufacturer we're using for the glass was capable of printing any kind of fruit pattern we wanted. And they didn't really care if there was a consistent panel or not, because it was a printer. It didn't matter if it was printing one pattern or the next. It didn't make any difference to it. So what we actually did was we developed a facade system where these panels over here are made of glass, and these are made of metal, and there's a frit that makes it look like this monolithic material. And then we looked at what kind of pattern we would create. We've used different kinds of frit patterns and dot patterns to start to create this very gradual blend between the two. And it just kind of opened our eyes and made us start thinking about the fact that depending on what your process is in construction, you don't necessarily have to think about mass production. Because if it's a printer, it doesn't care. And then that sort of evolved into the next series of projects. This is another project where we're basically looking at variation on the facade, but we're trying to rationalize it down to just a few simple components. I think the interesting thing about this project, though, is actually the roof. And I'll get into that, because that's really where digital fabrication became essential to pulling off the project. So let's see what I have here next. This is a little bit of I think this is a video that shows how we developed that facade. And let me see if this one will play. Some of these will play, some of these won't. It's okay. It's fun. Because I don't really want to talk about the facade. It's a point attractor. Are you guys familiar with point attractors? Anyone ever do those in scripting? Basically, it's a relationship between these points floating in space and those panels. the closer the points are to the panels, the more they're going to open up. So we can create this pattern by manipulating these points. So the point is that someone doesn't have to go in one at a time and change each panel, because now we have sort of a marionette. You know, it's something that with a couple of different controls, we can create all this patterning and all these effects. I wanted to return to that later, though, when we talk about Grasshopper. So really, I wanted to talk about the roof more. This one. So check out this roof. It's first of all, it looks pretty simple, but it was actually pretty tricky to model. You could do it in Rhino, but there was a lot of blends, and it ended up being this poly surface that was really hard to manage. If one thing changed, you had to rebuild the entire thing. So it wasn't really practical to work with it in that format. At the same time, we've got this kind of free-form surface. How do we manufacture and how do we document that in a way that doesn't freak people out? Because they're going to look at that and see this completely non-repetitive, non-uniform thing, and they're thinking in terms of manufacturing is about repetition. So we did our best. We sliced it a million times. We drew all the sections we could, and the price came in at 3 times what we could afford. It was 3 times the budget. So basically, we were at a point where there was 2 paths for us to take. One was we start to rationalize the system. We start to simplify it down to like really basic domes with a flat skirt and get rid of the whole freeform thing. Or we figure out how to fabricate this using digital tools. Fortunately, we got in contact with this guy who does the framing for all of Frank Gehry's interior walls. And he had it all figured out. He was the intelligence. He was the kind of the go-between between the like dumb structural shell of the roof and the finished surface of the metal panel. And the great thing was, all he needed was a Rhino surface. So once we got in contact with this guy, he basically had a setup in his shop where he could take the surface, he contoured it at whatever interval we wanted to, and he created these ribs out of light gauge framing. And he had a machine that crimped them to any shape he wanted. So all he needed was a path, really. So as long as we gave him a surface, he created the paths and he took it the rest of the way. He created a series of ribs on the roof that gave us that curvature and all the form that we wanted. And then on top of that, we put standing seam. And that price came in, so the first price came in was like $120 a foot for that roof. This price came in at $35 a foot. So that's in the budget. And we didn't have to give anything up. But had we not gone down this road, had we not found the know-how, we would have simplified it. We would have done the easy thing, the thing we would have done in the past. So that really got us thinking. These are some of the details for that project. Skylight. These are these, he calls them flicks, but they're just little pieces of light gauge framing which you kick into place. And those are the ribs that he brought, that he would produce and bring out to the site. And that's the drawing for the roof. So what's interesting about this is that this drawing doesn't make the contractor feel that good. Contractor pricing this, they see a lot of contours and they get really nervous. High prices come in because there's unknowns. I mean, if you don't know something, it scares the hell out of you, so you mark up the price as high as it can go. But once you do quantify something, then you can price that accurately. Even if it's really intense, even if it's really difficult to pull off, you can put a price to it. It's not so scary. And that's the lesson we learned from this, is that once we had the system in place, and those people could price the system, we got to a point where everyone was happy. If we had never got there, we would have just made a couple of domes, and I don't know what we would have done. We would have had to change it significantly. So the project after that one was Jacobs Medical Center. This is a hospital in UCSD, UC San Diego. It's a pretty large building. It's an all-glass building that has a frit pattern on the glass, and it has kind of a device on the facade where there's these cuts into it that are positioned strategically based on solar data, and that allow it to perform in terms of the heat gain. So having had the frit experience on the previous project, we said, well, we can print any pattern we want on this building. There's really no limit to it, so why not really explore what a connection could be between the movement of the sun and the frit pattern on the building is, and really link those things together. So that's when we started getting into analysis. So analysis, just like we're using Ecotech with this one, which is an okay analysis tool. I don't know if anyone's had any experience using Ecotech. Anybody? Yeah. Has anyone used any other analysis tools? Like just anything? Structural analysis, environmental analysis, anything like that? Yeah. Okay. Well, I don't know what your experience is, but when you first get into those tools, a lot of times they're telling you tons of stuff and you don't know what it is, right? Like you don't know what the metrics are, you don't know what the data means. So the first step is really to try to figure out what it is you're getting. And then you don't actually know if that tool is giving you accurate data. I mean, that's something we take for granted. A lot of times someone puts a piece of software in front of you, it looks really fancy and it's got great charts like Ecotech, but no one's actually tested it. Which, I mean, it blows my mind, but it's true. No one's tested Ecotech. It's not a validated piece of software. It's giving you information, but no one knows for sure if it actually reflects reality. We didn't really question it all that much for a while. We just used it to kind of create comparative analysis between different runs. But eventually, we kind of, enough people were asking tough questions. We're like, we better figure out if this is real or not. So we switched. We use Diva now, which if you stick around for the next later session, I'll show you guys how that works. But that's a validated tool that's been tested and proven and tried, and there's been post-occupancy analysis to show that the data you're getting out of that is useful. Anyway, so I digress a little bit, but the point here is that we're trying to link solar radiation data to the frict patterns that we're studying and directly connect the form of the building with the data we're getting from the analysis tool. So you can see that the patterning of the facade and the frict pattern work with the kind of the form of the building too, where we have overhangs. So all of these systems are starting to work together, and that's partly because there's someone behind this who's doing the modeling, who's using Grasshopper, who's got this thing kind of all wired up. He's funneling in data from Ecotech, and he's funneling in modeling data, and he's making everything kind of synchronous. And this is a script that was used for those different patterns. And, I mean, we're really able to get into it because the kind of compromises I was showing you earlier, where you have a window and it's kind of like at the floor, or it's really high, because it looks good on the outside. Now you have a really flexible system where you basically can make it do whatever you want. You still have the effect of the texture at the end of the day. So that opened up all kinds of new doors for us. We got really excited about this. This is more just the ability to get data out of your model. And we actually print all these frits and tested them. They frit all over the office for days. Every piece of glass surface was covered with a frit pattern on it. So, having gone through those projects, we realized there was a whole world of stuff that we needed to get into and explore. And do that on a more of a research, scientific way that doesn't necessarily connect with the project. And that's really the fact that we can now have unique panels on the facade that are connected to anything we want. Anything that we want to drive the exterior. So whether it be daylight, or wind, or solar radiation, or views inside, or privacy inside, all of those things together, we could create a model that puts all those factors in. And maybe it doesn't tell us exactly what the design is, but it just informs us. We make better decisions because we know what all those things come together to produce. So that was really the goal of the Paratonic Surfaces research. It started us off, and that's what started the blog. We looked at buildings that were already kind of doing this. We kind of categorized them into two categories. One, which is buildings that are fixed, but are fixed in a way that's responsive to their environment. And another, which buildings that have active facades that they can actually physically move using sensors and actuators and adjust to climate changes and whatever is happening today. So on the left is a classic example of an active system. This is the Jean Nouvel Air Institute. As soon as you show this project anywhere, people go, "Aren't those broken?" Yes, they're broken. They've been broken for a long time, and it's really not about them being broken or not. It's more that it was something that he attempted to do, and it had meaning that went beyond just the fact that they were performing for sun. But the fact that he was trying to use sensors and connect that to actual weather that existed around the building was pretty remarkable for, I think, 1989. This is the ThyssenKrupp headquarters, finished about 2 years ago. These are these metal feathers that can fold in and out. so they can adjust to local climate conditions. And then, signal tower, classic example of a building, it's fixed in place, but it's adjusted to meet privacy or public areas inside the building, creates an effect on the exterior. So it's responsive, but it's responsive in a way that is fixed. And then projects that were under construction and are now, like this one's finished. I don't know if you guys have seen this one, but these, all these panels push in and out like umbrellas, and they can open and close. It's in Abu Dhabi, which makes sense. There's a lot of sun there, so solar heat gain is a big concern. Fair Tower, I think, as a whole. This one I think never happened. And then we started seeing systems that were basically products. They were off-the-shelf products. So like this one over here, this one was more of a research thing. Very cool though. If you've ever seen the video, it's amazing how this kind of morphs into that. And it's really just two pieces of dissimilar metals. One heats up faster than the other, and they basically expand like a lung. And so you get a more opaque glass surface when that happens. So it responds directly to heat. Then there's Obermann Associates and the kind of stuff that they're doing. And then Solidigm and Sage, which are electrochromic glasses, which will tint on which kind of suck. I don't know if you've ever seen those in person, but the panels of glass are really small so far, and they don't look that great. But the technology is getting better. I mean, it's something we can expect to improve over time. The mullions are hugely thick, as you can see, and all that bad stuff. But definitely something that has potential in the future. So how is this any different than what you're taught to do in school or what we've been doing for the last 100 years? I mean, aren't we supposed to be making responsive buildings? I mean, aren't you supposed to put horizontal overhangs on the south side and vertical fins in the east and west and make your building the shape and all that stuff? Yes, but what we're talking about is a fine-tuned building where every panel can be slightly different based on its exact location. So if we can tune every single part of the building to its specific location on that building, how much better can we do performance-wise than we could just using these kind of generic strategies, one-size-fits-all kind of strategies? Especially now that we have the tools and the construction methodologies to produce those kind of buildings. So this kind of idea where you've got a series of panels, and this is pretty much just a decorative screen, but it is a demonstration of how you can create variation to be responsive to any climatic condition you can choose. So how do we develop those systems? They are complex. Every panel is different. We can't go one at a time and model every single panel where every single panel is unique. It's way too labor intensive. So we need to start developing ways of dealing with this data that is like a marionette. You can create a lot of movement, you can have a lot of control, but you're only manipulating subtle points. You really don't have time to go in piecemeal and model it the way you would in the past. You need things like Grasshopper, or things like 3D Studio Max, or things like anything else that gives you the ability to control things parametrically, and also the ability to create links between things. Like I don't have to call Revit a parametric software. You can do this, but you have to really cheat with the system. It's not. It's parametric in that there are parameters, and you can change things with those parameters. But you need more than that. You need relationships. You need to be able to create relationships between one object and another, and you need to be able to create relationships between your model and anything else in the world. Data. You have to be able to link those things up. So we started off the research by doing some simple proof of concepts. Really basic stuff that we did in like 5 minutes. The first one was, can we link an environmental tool with a 3D model and have that 3D model change based on the analysis that's coming out of the environmental tool? So that we did. We used a plugin called Gecko, Grasshopper, and it linked to Ecotech, and it was great. It worked. It was pretty brilliant, and we were really impressed. So what happened was, each one of these panels had a little aperture, and those apertures are being controlled by the radiation on the panel. So where it's hot, those little holes are small, and where it's cool, they're really big. And we didn't do that. We just defined the system. It happened automatically. So those are the kind of relationships I'm talking about. That's what we need to create to be able to pull this complexity off. And this is all going back to the managing complexity thing. It's It's being able to create it, it's being able to understand it, and it's being able to explain it to somebody else. So these are just examples of parametric tools and different ways of feeding data into the model. So you can do that with an Arduino controller and a sensor. You can do that with an entry, a point of entry in a software package like Max or Grasshopper or Revit. You can do it 100 different ways. So we did another proof of concept, which is using a sensor and Grasshopper and a 3D model in Rhino. And if this doesn't play, I'm going to open it up and play it separate. Let's try it. Just give me 1 second. So what we've got is Arduino board, a bunch of sensors. That one was the wind sensor, and Grasshopper, which models the balloon. So everything's linked up. Wind's blowing, Grasshopper feeds data into Rhino. Rhino builds a balloon that blows up and acts like a balloon. And it's all just a bunch of little off-the-shelf components that aren't really that big of a deal. The proof of concept was this isn't that hard to do, and it's not like space-age technology. It's around and available. So definitely interesting for us. Unfortunately, I'm going to have to keep doing that for the presentation. So yeah, I want to show you guys this one too. Is anyone familiar with Galapagos? Yes. Okay. So for those of you who are not familiar with Galapagos, this is another way of parametrically modeling something. But this is a tool that we can use for optimization. The way it works is pretty simple. It's a kind of a good analogy. It's kind of Darwin's theory of evolution, right? So what it does is it tries 100 different things. Say you wanted to make little triangle box shapes like that. You give it 4 ways of doing that, and using those 4 ways, it's going to try 100 different variations. And you're going to tell it that I want you to make the one that has the least amount of surface area. That's what you're calling your fitness. So you define ways of making the box and fitness, small surface area. Then Galapagos takes those 100 random things that it's tried, and it looks for the ones that are the best. It takes genomes from the ones that are the best. Those are those little parameters, and it sees which ones correlate with which other ones, which ones correlate with themselves, and then it creates a master genome. So what it's doing is, rather than brute force solving for something, rather than trying every possible option of something, it's going to first try a bunch of random ones, and then with each successive generation, it's going to get a little better. So it's a fast way of doing optimization, much faster than brute force, which is, brute force can take you a week to do any kind of analysis. Galapagos can do an optimization in an hour, 2 hours, overnight. So I'm going to show you a video that we did with it. So now we're tying 3 things together. We've got our genes, and these are building a cone. We've got ecotech, which is doing a solar radiation analysis on the cone. And we've got Galapagos, which is trying out all these different iterations automatically. So what it's going to do, it's going to try making different cones. It's going to make 6-sided cones, and 8-sided cones, and cones that are like this open, and cones that are like that open. And it's going to measure every single one with ecotech to figure out what the solar heat gain is on every single one of those. And then it's going to figure out which of these parameters are doing the best in terms of minimizing that heat gain. And successively, over some number of generations, it will give us the most optimal solution to that cone. So, I wish my links were broken, but it is. Not sure. Not yet. We're not there yet. We just told us we could have at the end of the presentation. Yeah. Okay. So this is demonstrating what I'm talking about with the genomes. These are the options that it has to try out to make these different cone shapes. So it's got one that controls the top, it's got one that controls the bottom, and it's got a lock between the top and bottom. So we've got those as genomes. Now remember, our fitness is lowest amount of heat gain from the sun. So you start Galapagos, and it starts testing. This is not real time, but it's close to real time because we had the settings really low, and it was a proof of concept. So now the computer's automatically iterating for us. It's going through thousands of options, and it's going to tell us, in this case, because we asked the dumb question, it's going to tell us something that we could have figured out on our own. But the point is that it all works, and we can use it to solve much more complex problems, and at least inform us when we're making design decisions. So that shape probably looks pretty familiar to you. It's like an air traffic control tower, and that's because air traffic control towers are meant to block glare from the sun. So it's basically trying to shade itself as much as possible, and it's also reducing surface area as much as possible. Now we run it backwards, but you get the picture. So we sort of proved that this could all work and that we could use these tools to inform design decisions. So then we took it to the next level. We said, what if we just did a project where the entire project was based on relationships? The entire thing is a grasshopper definition. Everything is driven by views, solar radiation. It's all based on data. I mean, there's design going on too. Don't get me wrong about that. But it's all being informed by the things that we talked about. So the structure, the skin, the energy modeling, and the rationalization is all built into this definition. This was a stadium project, so what we did is we took the code book and we actually have in-house stadium experts, and we fed all that into Grasshopper. So the seating was arranged completely prescriptively by the code. Usually it takes an expert, you give it to them, and they come back a week later for one particular design. It takes them a week to lay out the seating, and here it is, and it's this very genius thing that they did, and it's like secrets about how you do it, and you get the view corridors and stuff. We fed all this into Grasshopper, and it was just spitting them out. As soon as you draw the curve, there's the optimal seating arrangement. So it's the kind of thing that really changes the way the entire industry works. So as you can see, we're drawing sight lines to the field, and that has us optimally positioning all the seating. The shape itself is it was created entirely in Rhino. It's T-splines, and what happened is that we start to create panels. We look at the solar radiation on that form, and then the panels are informed by the solar radiation. So it becomes this big canopy. And where you need more shade, the panels fill in. And when you need less shade, the panels aren't full. Driven are influenced by Arabic motifs. And you can see the solar radiation information coming in. That's parsed into 10 groups, so 10 panel types. And then those 10 panel types are dispersed around the surface. So we've got the 10 zones here and the different panels. So it thins out as there's less need for shade. By the way, what's interesting is when you take just raw material and you look at the raw material it took to get to this level of sophistication, you're talking about like a 40% performance improvement because you put the material where you needed it and you took it out where you didn't. If we had done a standardized panel, we either would have used more material or we would have had, the performance wouldn't have matched. So something to think about. The other thing that we looked at was where we have the most curvature, we probably need a curved panel. Where we have less curvature, we could get away with a flat one. That's another one of those pulling it off kind of scenarios where flat panels are cheaper than curved ones. So if we can minimize zones where there's curves and just have curved panels where we need them, that's something that would help us achieve get the building built. So all of that kind of shows that the different relationships between solar radiation and panelization. And then we started to try to experiment with documenting that graphically. So showing all this data in a chart. This chart, I'll be honest with you, doesn't tell you much. We're just practicing, and it's first stab at something. So it's really just a bar chart that's wrapped around a circle. But you'll see in later iterations we've made this a lot more meaningful. And that's the resulting project. It was a competition. We unfortunately didn't get it, so this one didn't happen. This is a project that is happening. It's under construction now. They're just starting construction on this scrim as we speak. So this project was pretty much the same idea. We had a lot of glass in the exterior. We had a metal scrim, and we wanted to open up apertures where there's views and where there's big spaces on the interior. At the same time, we wanted to shield the building from solar radiation glare. Skylight in the middle, it's a view inside. So that was our proposal on the project. We got the project. We were very excited. And the chairman of the company, this is for a company called CJ, by the way. Anyone who's from Korea would know the name of the company because they're like Coca-Cola in Korea. They make everything. They make medicine. They make food. I mean, they're a huge company. So the chairman is like a big deal president kind of guy. And when he shows up at the building, there's people stand like very far away from his car and all this kind of stuff. So he came to one of our meetings and he said, I need an only one kind of concept. We didn't really know what that meant, but roughly translated to something like, I need something that's completely unique in this building. So what do you got? So we already had this kind of aperture skin system, and we proposed that he do a kinetic system where these things open and close like eyes. And he said, okay. So then we were like, oh, how do we do that? I'll show you an example of what that could look like. We showed him this video, and I mean, I don't think we really thought he was going to go for it, but he did. So we were looking at the Gina concept car a lot. I don't know if you guys have seen that. That's the BMW concept car with the fabric skin that kind of it can morph basically. It's pretty amazing. Unfortunately, it's made out of whatever says this. It's very hard to find out. Spandex. The car is spandex. Yeah, I mean, it's so funny because I was doing this research and I was like, they must have developed this really awesome material to be able to do that. This high-tech material. All we need to do is find that same material and we could do the Gina concept car just on the building. And I kept researching and researching, and I found out it was spandex coated in like polyurethane or something, and that the car stays inside or piece on. So that wasn't going to work for us. We did do a lot of research on kinetic facades, and I'll get into that later. I'll tell you guys kind of where that went. Long story short, it's not a kinetic facade building; it's a fixed facade building, but it is optimized, and we did do all the stuff that we talked about. It was modeled parametrically, but this time we used 3D Studio Max. It's kind of the same thing, it's just a procedure. So we were able to control where these apertures happen really easily with just a series of steps. That's recorded in our modeling process, and then each step is something that we can tweak. So I'll just go through this quickly, but that's basically how every band is modeled. That's a video that you can watch it. And the way that we modeled it was really analog, like really low tech. We basically took the floor plan and we put it in the file with the solar radiation data and manually put the apertures where they made sense. There was no magic to this. I wish I could say we did a grasshopper script and we figure out what big public spaces were with the apertures right there, but that's not how it happened with this project. And this was like 3 years ago, so we're getting there, but we weren't there at this point. The intent was there, though. The intent was to make this high-performance facade. And so what we did was we built these masses wherever there was a big open public space or open office space where they needed more light. And we overlaid that with the solar radiation data, and we used that to design the facade. At the same time, we started looking at what that data meant. Now you notice, like, whenever I show you one of these colorful solar radiation images, you don't really get what's going on the backside. And that's like the worst part about these things, is they're great if I have a 3D model in front of you and I can spin it around and you can kind of see what's going on. But there's really no way to get a sense of what is happening to the building from 360 degrees. So this was our first effort at creating a two-dimensional, one-frame graphic that represents what you're seeing here. So each of these circles is a panel on the facade. And the amount it's displaced from the center is based on the amount of solar radiation it's receiving. And the direction it's pointing is the direction the panel points. So by looking at the chart, you see I've got the southeast orientation is a big problem. I've got a lot of area there. So that's something I might want to address. And then I do the same analysis for a pleated version. This is a continuous pleat. It doesn't have any of the variation I showed previously. We compare that. And we see that we've dealt with a lot of that bad stuff happening on the south-southeast. And actually, we reduced the solar heat gain on the facade by 54%, which is huge. I mean, that's a crazy number, but it's because we basically wrapped it in another skin, so it's kind of cheating too. And then finally, we optimize it by putting in these apertures where we think we need. Okay, and then you say, big deal, you got 2% more, and you put in all this effort and all this cost into this skin that's completely irregular now. Was it worth it? And the client said the same thing, by the way. And it was really tough because we had to make this argument and we didn't have data to back it up. The argument is that I'm only showing you heat gain. I'm not showing you daylight. And daylight is actually more energy cost than you spend on cooling the building. So if I can let more light into the spaces that need it, and we can dim the lights inside, I can save you more energy than I would by just putting shades everywhere. Unfortunately, Ecotech can't do that calculation. The daylight calculation that Ecotech did used this like generic cloudy sky model, and this kind of like fine-tuning is completely transparent to that analysis. So we were pretty distraught to find that out, and this is kind of one of the reasons we moved over to DEO, because now we can do that calculation, and we can sort of give people a more holistic idea of the pros and cons of say, doing something like this. Fortunately, that took us on good faith, and we moved forward with this design. But, I mean, it's a really good example of how it could have not gone that way, because we weren't armed with the right tools to be able to make our argument effectively. This is an explanation of the chart that we just went through. Another rendering of the building, getting in closer on the skin. So we went with an aluminum skin, perforations that vary depending on the orientation. That was done in Grasshopper. We scripted it so that they flow with the curves. It's pretty cool to see it close. And some details of the system. Another really cool thing about this building is we didn't have any mullions in the building. Completely eliminated them. We worked with Arab, great engineers, and they helped us figure out, it's called a strong back system. So there's actually a big steel truss up there in that plenum space, and that makes this part stiff enough, but you don't need any mullions. The glass is super thick, it's like an inch thick, and it's extremely expensive, but it's also completely open. There's nothing blocking your view, and they have great panoramic views all around the building. That's the glass section. It's two pieces with PVB, inner layer, airspace, and then another piece with a light of glass. So almost 2 inches thick, about 50 millimeters. So that's crazy. This is how we did the perforated panel on perforated pattern on the facade. We basically brought the Max model into Rhino. We converted the surfaces into surfaces. Converted the meshes into surfaces, and then we ran the script on it and generated a series of panels that then a manufacturer can cut into each aluminum panel. There it is under construction, and that's the I think that's the accepted mock-up of the skin. So as you can see, a lot of complexity here. I mean, there's a ton of variation in the panel size. The holes are changing. It's basically every panel is unique. It's not every panel is unique, but there's something like, I think, 200 some unique panels on the project.
So how were those manufactured?
They're actually manufactured flat. and they're just cut so that they're basically unrolled in Rhino. And then there's plasma cut out of a big piece of aluminum. And then the holes are punched in. There's a punch that would punch in the holes.
Those are, because it looks like there's
undulation. Yeah. So it's actually flexible. It's super thick. You wouldn't think it's flexible. It's maybe like a quarter-inch thick. Probably even thicker than that. But it's aluminum, so it's not super heavy. And when it's in big enough pieces, I mean, this piece right here is probably like 15 feet long, you know? So when it's that long, when you lay it down on a steel tube, it'll conform to the tube. So it was literally, this is an unroll in Rhino. And then that's the cut pattern, and then they punch in the holes. What I should say is that we had the design model, but then the manufacturers came in and did another, we built the model in Digital Project, which is the tool that Gary uses for all this stuff. So this is a case where we didn't really have the documentation necessary. It wasn't detailed enough to produce this. And this happens a lot. I mean, a lot of times manufacturers go in and rebuild your entire model just to pull information that they need. And that's actually really important. I mean, that's one of the more interesting things I'm finding. I'll get into it in the next project, is that if you can communicate directly with the manufacturers, you're a lot better off. I mean, you can save weeks, if not months of time, but you have to know what language they're speaking, because everyone speaks a different language. And if you as the architect know how to translate your work into those different languages, yeah, you can really get ahead. We're going to do kinetic facade. How am I doing on time, by the way? Because I can talk forever.
You could say a little less than an hour.
A little less than an hour? So maybe like 15 more minutes? Everyone hang out for 15 more minutes? Okay, so this is the kinetic facade part of the discussion. This is the project I was telling you about in Abu Dhabi. We worked with the engineers. The guy, Matt Williams, who works at Arab, who's the leader of the facade group, came over to us to help us out with CJ. This is a PTFE, which is like a fabric. I think PTFE is, what's that Tupperware material? What's Tupperware? Tupperware. Anybody? What? DuPont. It's basically like a fiber, like a nylon fiber covered in Tupperware. That's ETFE. I couldn't believe it. It was really good. It is. Anyway, so this was the system that he started with. These are some of the sketches he did for us. So basically like an umbrella. And it had a linear actuator in the middle that would push out and sort of do the folding thing. But it wasn't kind of doing what our design was doing, which was really being more of a pleat. It was just a single fold. So we tried to work with them to sort of get back to more of the folded thing. And he had this idea of a traps. But I was really sort of enamored with the umbrella idea, and I was hoping that we'd push that. So I looked at, I found this old, like Grandma Burberry umbrella, and it had this mechanism in it that was just totally awesome, and it was doing exactly what we wanted to do. So we looked at how that worked and used that as the inspiration for the system. It's basically a linear actuator with that on the end, and it's like a hinge system. It works just like an umbrella. So that was pretty cool. I think Matt was really into that, and that was actually where we left off. We're going to start to develop that in elevation. We had sort of figured it out in section already. To sort of prove the concept on that one, I modeled it in Max with a bunch of animation tools because people don't really believe things until they see them for themselves, and that was one of those things where it really made a difference. So essentially what's happening is you have a linear actuator right here and a trap right there, and this arm is pulling on that arm. So it's a pretty simple system. It's not anything that out of the ordinary. It's just these 2 linear actuators. The problem we were having was with the material. We didn't have the material at the time to put on this that could do the stretching, would stay taut. Mehrdad was really focused on keeping the look of the building, so he didn't want to sacrifice the aesthetic, which was this kind of taut, sheer scrimp over the entire building. And because it had to constantly stay taut, it couldn't do what the umbrella is doing, which is fold up and crinkle up. We didn't really have that material to do that. So we sort of moved away from that kinetic system and we went back to the metal scrimp. Which, by the way, they did actually give us the choice. I said you could have a kinetic system, but it's going to be like a bunch of little garage doors that open and close, and it might open and close separately from one another. And it was like, kind of tempting still, even though it's totally not our design. It was like, but it would move. The whole building would move. But of course we didn't do that. So anyway, I'm going to do one more project. I think that it's pretty relevant, and then call it. So this was a competition for a new federal courthouse in downtown Los Angeles. This was we did last summer, I think. It was interesting in that you teamed up with a contractor. You had a couple of months to do it, and at the end of the competition, the contractor put in a price, and they were stuck to that price, which was a pretty low price. There was a price range that's given to all the teams, and you could be at the high end or the low end, but it was pretty constricting. So that was one of those things where you're designing and you have the contractor standing over your shoulder saying, no, you can't do that because I don't want to be on the hook for that. So everything we did, this isn't something that you could say, you know, we're going to post-rationalize it. It looks really crazy now, but trust us, later on we'll make it really simple. Because they're not going to take that risk. It doesn't make any sense for them. So we had to really work with them. And I'll tell you guys the full story. But first, the initial impulse was to orient the building with this orientation to the north. That's north is kind of up and to the right. And we looked and we studied which orientation was optimal. This is really interesting. If you look at the baseline, you get a 25% reduction by rotating at 60 degrees. But if you know that you're going to have vertical fins on there shading it, that's not the optimal orientation. The optimal orientation is you get a 31% reduction if you orient it, what is that? Solar. Well, you orient it that way. So this is something that happens all the time. You go through step one, it's the massing, right? You figure out what's the optimal orientation for my massing. Okay, now I've got that. Now what's the facade system doing? Okay, what's the optimal facade system? But if you can do both of those things at the same time, you will get a better answer. The thing is that because we often go through kind of a linear process, you can never optimize it to that point. Here's something now where, you know, because you have tools like Grasshopper, you can instantiate a bunch of geometry like that. You can study orientation and shading together, and you can do that on day one. And because you can do that, you can make better decisions. So the building was sort of inspired by these verticals of vertical fluting on traditional columns. We used that as an opportunity to create shades and privacy and variation in terms of porosity in the building. It's a very rational plan. It's this triangle-shaped courtrooms in the middle. It's extremely efficient. The contractors loved that part of it. The part they didn't love was all this variation because it looked to them like every single panel was different and that they would have to fabricate each piece individually. On top of that, it looked to them like every piece of glass would be different too because the building's tapering in terms of the form. And they didn't know what that difference was. They didn't know if they had 500 unique panels or 200 unique panels, and that scared the hell out of them. They weren't willing to go forward with that. This is sort of explaining what the system is doing. You can see that the vertical fin, as it pushes out, it pulls in. So you get more glass and more shade, or more insulated surface and less shade. How's it going? It's a close-up of what the skin's doing. You can see it's pulling out here on the end, casting more shade, Where here, I think this was like a stairwell or something, so we made the windows small, more insulation. We started to give the contractors data. We thought this could help, right? We can at least tell them how much material is on the building. That should help them give us a price, right? It didn't really help us give us a price because it's too general. It doesn't explain the complexity. It's just about the material. So they don't really care if there's X amount of metal panel in the building. What they do care about is that every single one is different, and it would be months and months of fabrication time. So this wasn't really working. So as we were working and we were moving forward, we start to come up with a model that's completely generative. We've got building variables, and then we start to create different outputs. One of those outputs was a curtain wall schedule. So what we did was we scripted as part of the design, we scripted a curtain wall schedule where every single panel was laid out on a sheet. This gets generated while we're designing. So if we change the shape of the building, this entire schedule changes, it updates. The counts update, all of this stuff is updating in real time. This came out of really out of necessity. We were totally out of time. It would have taken their team 3 weeks to rebuild this entire thing in Revit, which is what they use to price their stuff. So I got on the phone with the people and I said, what can I give you? I can give you all this data. I've got it all, I'm all excited. And they're like, well, just give us the file because we're going to rebuild the entire Revit model. I'm like, really? Why? I mean, maybe we can give it to you in Revit or something. And they said, well, we've got this family that we use in Revit, and it spits out numbers of material, and it tells us how many panel types. And I'm like, well, why don't I just give you that directly? And we can save the 3 weeks because we don't have it. Because by the time you're done pricing it, we'll have changed it 3 times because we're in a design phase. So this is what we came up with. It was the panel schedule. And basically what you have here is a key that tells you how many unique panels you have. And it really boils down to just 12 curtain wall panel types, and there's 53 fin types. And even though that seems kind of high, and there's probably a lot of complexity in these ones down at the bottom where they're tapering, because we could quantify it, because it's a known factor, they could price it. And they did. And it turned out that's something that they could live with. And also, I mean, if you look, I don't know if you can see it that well, but like this panel type, this fin type, LJ, has like 2. We could have easily bumped that up to the next one up or the next one down and just had maybe either. I mean, if we had worked on this a little bit longer, we could have gone from 53 to probably 45 unique panels. It wouldn't have been that hard. So that's the kind of conversation that goes back to the original point I was trying to make, which is to pull this stuff off, you have to be able to manage your data, and you have to be able to communicate effectively. So that's really why we were able to put that proposal forward. If we hadn't had these tools, we would have dumbed down the system. We would have had like 4 panel types and 1 fin type, and it would have been a repetitive thing that you see every day. So that's the story with that. This is a closer look at what you were looking at with the little square. So each one of these shows a panel type. You've got, I think, everything from G, L, A through L. Tells you how many in every row, and then the fin type is down here. So an HH means it's an H profile at the bottom, H profile at the top. GH means it's shifting between a G profile and an H profile. And then we're able to catalog every single one of those and figure out, well, there's 50 combinations in the entire system. And we can probably get it down to 45. So that's how we do that. And then we produced one of these charts to show our solar radiation data, and now we're talking about daylighting as well. We still didn't have Ecotech at this point, so we had to just kind of like fake these. We had to fake them, and we really kind of just to suggest, because we kind of knew roughly that the rule of thumb that this is how it would work, but we're at least communicating the fact that you should be thinking about daylighting and you should be thinking about heating, that those two things are totally interconnected. Okay, so the last part of the talk is about optimization and automation, and I think that that's going to roll into the demonstration part. So if you guys want to stick around, we'll have a break first. Yeah, break. Yeah, so we'll do a break and then we'll come back and then we'll start. Oh yeah, yeah. Does anyone have any questions? Sorry.
Yeah. Okay. So I have that.
Yeah.